MS Teams. With a TUT email, you should be able to see them on MS Teams under the chat. So if you go to chat, you go to OPS, you'll see the videos appearing there. Who's not able to see them?
Well, sir, I can see them but can't download them.
Okay, by the way, do you have the 3 dots? Okay, I'll stop sharing my screen. Go ahead, share yours. Let's see. Share yours quickly.
Is it visible?
Let me see. Yes, it is. Okay, go to the 3 dots. Yeah. Open. The video will open. Then you should have it
You are on
downloaded.
LOD, not
Pardon?
OPS.
Say again.
He opened the one for LOD, not OPS.
Go back to the, how do you call it? To the Zoom chat again. You enter the chat of OPS, but you got a different video. Is that possible? That means you enter the chat of a different module. Yeah. Okay. If you go up, there's no recording.
Yes.
That's quite weird. What is it that is said on top there? Chat is
Muted settings.
It says this meeting chat is muted.
Yes.
Go to settings. That settings there. Unmute. Doesn't make any difference.
Yes.
Is there anyone else who's experiencing the same?
Yes.
Yes, sir.
Okay. Okay, I'll investigate about that. But at the same time, the link I sent you, what is the matter with that? You are able to access the videos at least through, because it's a OneDrive link.
Yes.
So it can still be an intermediate a solution while I find out why Teams is not showing on your side. Is that okay?
Yes, fine, sir.
Okay, let's carry on, please. Yeah. So last time we stopped, we were busy with chapter 1, whereby we introduced the concept of operating system, and we had looked at what an operating system is, what it can do, and we started looking at key elements or aspects that you wouldn't study an operating system without. And these include the computer system organization, memory organization, and the operating system structure itself. And we will look at the computer architecture, the operating system structure, the operating system operations as we go along. So we start by, we start where we left last time, and we had just discussed 1.2 we had just discussed 1.2.2, which was about storage structure. Now we will look at IOs, because as we mentioned, there are key elements that you can't do without when you speak about a computer system, and those include input-output structures, of course, because computer systems need to get data in, and that is done most of times through input ports, and they need to take data out, and that is often done through output ports. So we shouldn't confuse, and I insisted on this, we shouldn't confuse the input and output modules which are within the operating system, in the form part of the operating system, with input and output devices. Input and output devices are devices that we connect now onto the computer system through these input modules. Okay, so storage is only one of many of I/O devices within a computer. A large portion of operating system code because remember, at the end of the day, an operating system is a
Can you share
program.
your screen?
Yeah. Okay. A large portion of operating system code, I'm sharing it now, is actually dedicated to managing IOs. So, as you know very well, operating systems are used for managing resources, and some part of those resources include input-output. So, there's a big, besides managing memory, which is one of the resources, there's a big portion of the operating system software that is dedicated to managing input-output. Is my screen visible now?
Yes.
Okay. Yeah. Okay. And this is both because of its importance to the reliability and the performance of a system, and because of the varying nature of devices. Very critical, both reasons. First of all, the importance of reliability and performance of a system. The performance of a computer system, strongly depends on the input and output. Actually, the reliability as well. If you've got a computer system on which you can't acquire data, it's almost not a reliable, it's definitely not a reliable system, almost a useless system. So you want the acquisition of data to be reliable. Reliability also means that the data must be correct. You don't want someone to type on a keyboard 2 and then the computer system, through its operating system, handling that input, interpret it as a 4. Because if that is 2,000 rands and then it's interpreted as 4,000 rand, let's say of debt, then that's a big problem. Then in a banking computer system application, just to give that example. But the second reason is equally as important because of the varying nature of devices. So we know that input and output devices are, although they are standardized in terms of the communication methods they use to interact with the computer system, they are varying in nature and they are from many manufacturers. But at the end of the day, the operating system still has to handle their functionality despite their diversity. So that's why we're saying a big portion of the operating system code is dedicated to managing IOs because it's quite an intensive and complex task. Okay. Next, we provide the overview of input and output devices on a computer system. A general purpose computer system, and this here we're talking about your typical personal computers, of course, consists of CPUs, multiple device controllers. So when you speak about device controllers, you understand that these are input-output modules, as I called them earlier on, that are connected through a common bus. So from within a computer system, of course, you've got a CPU, because you can't speak about a computer system without the central processing unit. Okay, 1 second. Can you guys still hear me? Welcome, CS. I think it's your first time attending. Where have you been? CS? No. Okay. Keyboard controller, for example. Some of these input-output controllers would include a keyboard controller, which would be made of a encoder, decoder, right, type of circuitry. You've got your mouse controllers, all your USB ports controllers. Just to stick to the operating system within the context of a personal computer. But if you go microcontroller, you could have your UART modules. You could have SPI module. You could have a timer module, because most microcontrollers have got internal timers. And nowadays, you even have microcontrollers with ADC internal module, for example. So the communication between the CPU and all of this is done, of course, through a bus. I mean, through buses, through a bus actually in this case, and that specific bus that handles this communication is actually the system bus. It's when it comes to memory that we've got the, two buses, depending on the architecture in which we are. You often get an address bus and a data bus separate in Harvard architecture, but you get them to be common or the same bus, sharing the same bus in a von Neumann architecture. But in this case, we're talking about the system bus, which is the bus that handles communication between the CPU and the different controllers. Okay, so that is critical. Now, yeah, so you understand the motivation why I/O structure is a very important part of an operating system, because for those two reasons that I had given. So now, depending on the controller, more than one device may be attached. So, for example, if we take the case of a USB controller, the USB controller within a computer system may lead to 1, 2, 3, or more ports, in which case that will mean that the controller has got a hub mechanism, because I assume you guys have done some networking. A hub is just a splitter. At which layer is a hub a splitter? Let me ask. Let's ask CS. No, CS, are you there? Okay, Maluleke, at what layer is the hub a splitter? At what network layer is the hub used? Tiba?
I think layer 1.
Layer 1, which is physical layer, right? Just to link this concept to your other subjects. Okay, it's very important to mention that, because yeah, and that was just in bracket what I wanted to mention in terms of how it relates to network. So in such a scenario, the controller within the computer system will have a hub functionality, because it should be able to control more than one input or output devices. In the USB scenario, that would be it could be input or output devices at the end of the day. Okay, so that is what that sentence was trying to emphasize on there. Okay, so for instance, 7 or more devices can be attached to what we call a small computer system interface. SCSI is also an interface, similarly to the USB that I've just mentioned now. You may not be very familiar with the SCSI, but the USB at least is a familiar example. Okay, so a device controller maintains some local buffer storage and set of special purpose registers. Okay, so there is localized memory at the device controller level. That is what I'm trying to point out here, is that most of times your device controllers will have its local buffer. I'll give a typical example. Let's say you've got a Bluetooth module, meaning a Bluetooth controller within a computer, and of course through the operating system, for all the way from the software application, all the way from the application through the operating system, through the kernel, you want to speak to this Bluetooth controller, okay, and of course send data out. Besides the memory of the computer system, which is linked to the CPU through a different set of buses, the Bluetooth module in this case might have its own personal registers through which the CPU can actually give it instructions. Let's say that the communication between the CPU and the Bluetooth module is done by means of commands, or commands. So then the CPU will send commands to the Bluetooth module, which will those commands, of course, have to be received in some memory or some storage type. So that way the registers will intervene. So they will be received through some registers that are within the module, and then they'll be executed by the controller. Because remember that at the end of the day, the controller is an embedded system, meaning it's made up of hardware, but also some firmware. And that firmware within the controller, of course, talks to certain peripherals, to certain registers within the controller. Another very good example would be a suddenly interrupted, for the operating system to handle a suddenly interrupted Bluetooth communication on the receiving end, for example. As data came in and there was a network issue, or for any other reason, data was not fully written all the way to the memory of the computer system, you might need, if there's a buffer, there's a buffer register at the Bluetooth module level, then the CPU can pick up that something had come into through the Bluetooth module, but it was not it didn't fill up, or it is not completely sent to the Bluetooth device. I mean to the Bluetooth module. How does it know that? Let's take a typical example whereby the structure of the packet, the Bluetooth packet that's coming in, starts by the size, by the very early bytes of the packet is giving the size of the expected data. And then let's say that size says it's 40 bytes, but at the end of the day, when there's interruption, we only have 20 bytes in there. So then, based on the fact that the 40 value was received already at the Bluetooth controller level, then you would know, I mean, the operating system through the CPU, of course, and the Bluetooth controller will then be able to establish that a typical Bluetooth transaction was not completed. And that's how, at an operating system point of view, we'll be able to pop up a message and say, do you want to resume, for example, reception of that file or of that packet? Is that okay? So there is definitely a need for storage at the controller level when it comes to input-output devices. It just makes the life of the operating system much easier. Okay, and that's a typical example I've just given now. So that was very critical to mention. Okay, so the buffer storage or registers at the device controller level is critical for those reasons I've mentioned, but it also sometimes has a set of special purpose registers. And that links to the earlier example I had given, for example, in terms of command receptions from command handling from the CPU, or vice versa, from the input device or output device, because it could be going the other way around. You might need a special purpose register, meaning a dedicated register for a specific task. And this varies a lot depending on the input device or input controller we are talking about here. Okay. So the device controller is responsible for moving data between the peripheral devices, which I've been referring to all along as input or output devices. Peripheral is a good general term for both. That controls it controls and its local buffer storage. The local buffer storage, obviously, here we're talking about memory of the computer system. So typically, operating systems have a device driver, and that's exactly what I've been mentioning. So the device driver is actually firmware. It's firmware because it's a piece of software that controls hardware. And you will know that operating systems have evolved a lot with this respect. In the past, you almost had to install, on top of the operating system, you almost had to install drivers for anything. You have a new mouse, you might need a driver for it. You have a new, let's say, tablet, you might need a driver for it to be interfaced with your computer system. So these were additional piece of software that were added to the operating system to handle the interaction, to handle the interaction with an input-output devices. But now, with modern operating system designs, we have what we call plug-in. I mean, plug and go type of devices. Most IOs have become plug and go, and this is all thanks to the incorporation or integration of device drivers as part and person of the operating system design. Okay. So this device driver understands the device controller and provide the rest of the operating system with a uniform interface to the device. If you recall the hierarchy of interaction all the way from user application to the hardware through the operating system and the kernel, that exactly makes sense in a sense that as you go from the operating system through the kernel all the way to the hardware device, you go through an intermediate module, which is the controller, and the interaction between the controller and the operating system is facilitated by means of a device driver. Okay, that's just to recap on what we had covered already. So now, to start an I/O operation, input-output operation, the device driver loads the appropriate registers within the device controller. Exactly. So for input-output operation, whether initiated from the CPU side or from the peripheral device, there are some specific registers that often need to be loaded to initiate the interaction with the operating system. Okay. The device controller in turn, and that's why it has got some level of intelligence because it's made of a firmware, will examine the content of these registers to determine what action to take. These actions, of course, can include reading a character from a keyboard as a typical example, okay, or writing to a USB drive, or writing to a CD, or even sending information to a screen. Okay. The controller starts the transfer of data from the device to its local buffer. Once the transfer of data is complete, the device controller informs the device driver via an interrupt that it has finished its operation. Okay, so there is both signaling and the actual data transfer operations that the operating system has to handle as it interacts with the device controller. Signaling has to do with all form of instructions or how can I put it? All sort of control signals, yes, that are exchanged between the device controller and the operating system, such as start of transfer, end of transfer, notification, etc. And that has to be done when you think at the operating system design point of view. It has to be done by means of, it has to be handled as an event-driven, with an event-driven approach, meaning based on an interrupt basis, so that the rest of the operating system can carry on executing, and only when there is a specific action or interruption, the operating system can go out of its execution routine and go and handle that specific interruption, and goes back afterwards to where it was in its execution. So that's very important. And luckily, I'm talking now to computer system student, like the IT student I had last time. You clearly understand the concept of interrupt because you've had to deal with it in digital systems. Okay. So that's how interaction between the module controller, or also called the module device or controller, is happening between that. Sorry, that's how it's happening between the module controller, the operating system, on the other hand, and the peripheral device on the other hand. So that's how interaction happens, and all of that is coordinated and managed by the operating system. Hence, we insisted that the task of managing IOs is one of the critical and most, it takes most of the operating system function. Okay, and that's where we started when we introduced. So it's also very important that to improve efficiency, to improve the overall efficiency of the computer system, instead of handling IO requests or IO data transfers by means of interrupt, you can use what we call a direct memory access. Okay, direct memory access would be a mechanism for data to be written from the device controller all the way straight into memory without going through the CPU. Okay, what does how does it improve the performance, the overall performance of the computer system? Is that you save in terms of latency, you reduce further your latency or delays that would have been in transferring data first to the CPU and from the CPU through the address and the data bus to the memory and vice versa. So if you could go directly from the controller to memory, and then you have what we call direct memory access, and you would improve quite significantly the performance by reducing the transfer interval or the transfer duration. Okay, that is very critical. And that, of course, and now we're thinking in terms of actual implementation. The implementation of such would be, of course, only possible by means of buffers and pointers, as you could think about it. So already at the device driver, which is the firmware within, at the level of the device driver or firmware within the, within the device controller, we could make them point to directly to a memory, location, to a location within memory, and it can dump data to that specific memory and out, and also pull data from there through what we call direct memory access. Of course, the approach improves performance, but it has got a bit of inconvenience. What will be the inconvenience in this case? And to give you a tip, I will say, what will be the inconvenience in terms of memory management? Maluleke. What inconvenience would you think? What is the impact of having direct memory access in terms of memory management? Maluleke, can you hear me? Remember, we discussed that the operating system has got, among other tasks, the task to manage memory. And that we started by that actually, although we have a full chapter on that. We have mentioned already the task of an operating system in managing memory. So now I'm asking, the DMA improves performance, but what the overall performance in terms of processing speed and all of that of the computer system. But what is what I would say the cons of it, the drawback of it in terms of memory management? Rambuta, can you assist?
I'm not sure, but wouldn't it be mismanagement of memory from users? Maybe they would do conflicting things that waste memory, or I don't know. It wouldn't be that efficient, I guess, if we had direct access to memory. I don't know.
Yeah, you've got some pointers in your answer, but the point is really that at the end of the day, with DMA or direct memory access, there will be some dedicated memory then, which makes reusability of that memory not available to other processes or operations. Is that okay? So that will, DMA requires a specific piece of memory to be dedicated specifically for DMA operations. You get the point. So in terms of memory efficiency, obviously we lose a bit there because we can't reuse it. We can't have shared memory. In that specific dedicated piece of memory wouldn't be shared. Is that okay? Is that clear for everybody? CS?
Yes, sir.
Yes, sir.
Okay. All right. So that was very critical to mention. Okay, so that in how we interact between the device controller and the input-output device, as well as the CPU through the operating system, of course. So while the device controller is performing these operations, data transfer, control, and signaling, the CPU is available to accomplish other work. So that's the performance improvement aspect of DMA, is that the CPU is not involved anymore in transfer of data from the input and to the input device. I mean, from the input device or to the output device. because there's a direct memory access path that is dedicated for that. So the CPU could handle some other tasks in the meantime, and that improves the number of tasks handled per time, which means it improves the performance of the operating system at the end of the day. Okay, so some high-end systems use switch rather than bus architecture. Okay, and here I will link this again once more to one of your other subjects that you've covered, you've studied, computer architecture. So the bus architecture, of course, we define the bus as a set of wires. Well, I say wires, but in reality, we know that these are tracks of copper etched on a PC board. Okay, so in most computer systems, communication between the different components is handled by means of buses. We had mentioned address, data bus. We had mentioned system bus. Okay, but there is an alternative in terms of computer architecture, and that alternative uses what we call a switch. And once more, if you link this use of switch to networking once more, you'll understand that a switch sits at what level? Someone? Earlier on, we said that a hub would sit at physical layer. A hub sits at physical layer because it's assumed not to have a high level of intelligence. So it's basically pure hardware and more or less mechanical, or let's say hardware switching of some sort. Okay, a switch, it's one level higher. Is that okay? And that's it at what we call MAC layer. Are we together? So, and at MAC layer, it definitely has some higher level of intelligence. So when we say some computer system architectures use switches rather than buses, we're talking about a different approach to orienting data as it comes in from one module to another, or is it going out, depending on whether we're talking about input or output. Okay, rather than using the bus, because the bus requires, on top of in addition to the bus, we also require control signals. But with the switch, we can we identify each component by means of what we call the MAC address to a certain degree. So there has to be an identifier, which in this case will be the MAC address of every module. So the Bluetooth module within the computer system will be given a MAC address. The mouse driver or USB controller has got its own MAC address. If it's split in multiple USB ports through a hub, we've got different MAC addresses, and then the switch will each time, based on the MAC address, decide who the data is dedicated to and orient it accordingly. Okay, so that's an alternative to bus architecture. Okay, so now on these systems, multiple components can talk to other components concurrently. That's the other benefit. It brings in concurrency, which is parallel processing, meaning we are able to do. I mean, when I say I'm talking about the CPU specifically here. It's capable to handle multiple tasks at the same time thanks to the switching mechanism, because the different components are talking through a switch. They can each throw their data to the switch, and the switch will handle the switching or redirecting of that data to the appropriate destination device or module in this case, without necessarily having to make use of extra processing from the CPU. Okay, so yeah, so that's the key difference. The key difference is that switches bring in concurrency. The bus brings in the idea of sharing of resources, because indeed a bus is shared. The data bus, for example, it's the same data bus that is used to carry data from a USB, from a mouse that is also carrying data from a keyboard, and vice versa, from the CPU back to one or the other input or output devices. Okay, so with switches, we've got concurrency. With buses, we've got shared resources, which brings in the idea of one at a time, which is serial processing or sequential processing, that's the correct word. And between concurrent and sequential processing, it's clear that concurrent processing is much more efficient. Okay. So in the case of a DMA, when we're using a switch, it will be even more effective than it would be in the case of a shared bus. Okay, so let's look at figure 1.5, which shows how the interplay for all of these components happens. Okay, so if we refer to figure 1.5, we've got, well, it's applicable to modern computer system. And the modern part just to emphasize that we have the DMA implemented. So if we look at memory, which of course stores data, both data and instructions, and we've got an external device, any IO device, whether an input or output device, we can choose one. We can have a direct link from that device to memory, and that will be a DMA link. Okay. Alternatively to the DMA, would go through the CPU, which of course has in charge the execution of multiple of different threads and instructions. Let's put it like that. Okay, but when we go deeper and deeper in the module, we'll speak about processes, and we'll make a difference between processes and threads, because there is a nuance there. Okay, and the CPU then can interact with can serve as a bridge for interaction between memory and the device, and that will be done by means of control signaling and data movement. Instruction execution cycles, that's handled by control signaling. Data movement is handled through buses. In this case, the two buses involved are the data bus and the address bus. The address bus, sorry, to say where we are reading from or where we are writing to, and the data bus to carry the actual data we are writing to that memory location, or the actual data we are reading from that memory location. Of course, there's what I can call the up layer or low level storage within the CPU that we call the cache, and we've spoken about that. Which is a temporary storage interface between memory and the CPU. Data transit between that, and the sole purpose of cache, of course, as you know very well, and we've mentioned that, is just to improve the processing speed. Sometimes data doesn't have to be fetched all the time from memory, but it could be picked up from cache. If it's data that has to be used from one instruction to another. But the point is that that's just a bracket. So the point is the two alternatives are shown, either a DMA transaction or a transaction through the CPU, which can only happen by means of an interrupt signal, which is handled through the control unit within the CPU, handles the interrupt signal. And then we've got the actual, once the control signals are actually there to sequence everything, to say this is the beginning of transfer, this is the end of transfer. And of course, the data at the end of the day has to be transferred. And for that, we use the bus. And of course, the input-output request as well as the interruption are both handled by the control unit. So that's very critical. So those are the two options you would have as an IO interacts with a computer system. It either interacts directly through a DMA link with memory or through the CPU by means of interrupt. Any questions? Guys, is everything making sense? At least so far? Rambuda?
Yes, sir, makes sense.
Okay, Stiba?
Maybe it requires me to sit down with it alone, and yeah, it will make sense then. But for now, yeah, not really.
What is the challenge?
I think maybe it's because I haven't done this chapter and I haven't looked at it. So I think maybe after looking at it, I'll be fine.
Okay, but in terms of the assumed prior knowledge, in terms of computer architecture, for example, you're fine?
In terms of that, yes, sir.
Okay, so when I say CPU, when I say bus, you understand what I'm talking about?
Yes, sir.
Okay. All right. Yeah, all of these subjects are interlinked, and we feed from one to the other. So it's important to know that. And this chapter, first of all, as I mentioned at the beginning, is really just more like a revision. But it's trying to locate how the operating system, of which is the core matter of our subject, fits in the entire computer system. But we had to, of course, introduce and remind you of some of the basics. And that's exactly what we're doing here. Okay. So now, then we look at single processor systems. Okay. So once more, this relates to computer architecture. When it comes to computer systems, they can be single processor. They could be multi-processor. Okay. What do we mean when we say single processor? What do we mean when we say multiple processor? And the third category, actually, that I hope you also have covered in computer architecture, will be multi-threading, because there is quite a difference between a single processor system, purely single processor, and a multi-threading system. Okay, and of course, the multi-processor system. So let's start with single processor systems. Okay, most computer systems use a single processor, so it's the most common type. On a single processor system, there's one main CPU, so that's the key distinguishing aspect. There's one CPU, and it's that CPU that executes a general purpose instruction set. Of course, where are the instructions coming from? From memory, because they're preloaded in memory. And not only the general purpose instructions, but also instructions that are coming from the user processes. From the user processes means, in the hierarchy as we studied it, these will be instructions coming all the way from your application, from your user applications. Because remember, the hierarchy we went through, we've got an API, and from the API, we've got the operating system, just as a reminder. And from the operating system, we can go down to the controller, all the way down to the actual hardware. In parallel to this, of course, we can go to the disk, which is storage, basically. Okay. So there are system instructions. We'll refer to them at some point as system calls. And those have to do, I almost say they are auto-generated from the operating system. And there are user instructions. So that will be coming from the user application. Anything to do with your typical word processor or banking app. So at the end of the day, the CPU in a single processor system handles both type of instructions, and it's a single CPU. That is where the emphasis is. Okay. So almost all single processor systems have other special purpose processors as well. Okay. So this will be what I called last time hardware accelerated processors. Okay. So we've got one unique CPU, but we've got a hardware accelerated processor, meaning that's sort of taking out the task of the CPU and being localized, locally having some level of local processing for every module, for specific modules at least. So, for example, when it comes to the screen, you might have a screen interface, in this case. You might have a separate hardware processor additional to the controller of the screen, okay, that handles to pre-process, and that's the keyword, pre-process the data before it's actually processed by the CPU. But the point is, it makes the task of the CPU much easier because there's some level of special purpose processing that happens already at the controller level, okay. So they may come in the form of device-specific processors, such as disk, keyboard, graphic controllers, exactly what I was busy mentioning now. Or alternatively, this could be done remotely, and in that case, that will be done on mainframes. As you know very well, mainframes is the highest level of computing, at least modern computing. So as you go all the way from mini computers to mobile computers, personal computers, to servers, and from servers to mainframes. Okay, so you might have processing happening at the mainframe level, even at server level already, that it comes in handy to complement the job of this main CPU on the actual computer system. Okay. So they may come in form of more, of more general purpose processors, such as I/O processors, input-output processors, that move data rapidly among components of the system. Okay. So single processor systems simply means we've got a single CPU, but it doesn't mean that that single CPU cannot be supplemented by special purpose processors. Okay. All of these special purpose processors run a limited instruction set. Yeah, that makes sense because they are really dedicated for handling specific tasks. So if you think electronics, because you do electronics as well, you'd think of a special type of non-programmable processors, but mostly of ASIC, what we call ASIC. I don't know if you've heard about ASIC before. You also learn a bit about that in logic design, but I think logic design, most of you may not have done it already. So that application-specific integrated circuit. So this will be piece of hardware specifically designed to execute specific tasks. Is that okay? Yeah. So, but the point is the set of instructions that special purpose processors can handle is mostly limited. Okay. Sometimes they are managed by the operating system, in that the operating system sends them information about their next task and monitors their status. Okay, so the relationship between the operating system and these special or ad hoc or additional special purpose processors is simply to coordinate their action, rather than coordinate their interfacing with the CPU, because most the instructions are executed in this case at the level of these special purpose processors. The operating system just comes in to manage or coordinate their action. Okay. Yeah, this controller example is given there, and I've given the screen example earlier on. Okay, so that's more or less what we call single processors. Of course, with the emphasis that it's a single CPU, but it doesn't mean that's the only processing element. There could be additional special purpose processors working together with the CPU and managed by the operating system. Okay. So now, in other systems or circumstances, special purpose processors are low-level components built into hardware, as I had mentioned. That will be the case of what we call ASIC. The operating system cannot communicate with these processors. They do their jobs autonomously. Okay, so there's a nuance here. So we might have a purely hardware special processor. That will be an ASIC in that case, which just performs a set of instructions and does not necessarily need any coordination from the operating system. On the other hand, we might have a special purpose processor which still executes a couple of instructions, meaning it has got its own small processing abilities, okay, but it can only process a limited set of instructions. And in that case, the operating system will have to intervene to coordinate its actions. Okay, so yeah, it's just important to mention the distinction between the two. Okay, so the special purpose processors are of two types. They could be fully hardware, or they could be firmware driven, meaning they have a small processing unit on board, but only limited to processing a specific number of tasks. Okay, so that's about single processor systems. The alternative is what we call multiprocessor systems. But before we go to the alternative, can someone give me an example of a single processor computer system? Any? And justify why it is a single processor computer system in their view. Stiba? Stiba, are you there? Can you guys hear me?
Yes, sir, we can hear you.
Of course, a single processor system example will be easy. A single processor system is definitely, your personal computer is a single processor system, for example. Okay, I wouldn't go for a cell phone because modern cell phones nowadays happen to be multi-core, okay, or multi-processors. Multi-processing, happen to have multi-processing abilities. So not all mobile phones will be single processor. Is that okay? But a personal computer definitely. Although you can have dual processing on a personal computer as well, but in general, they are single processor systems. Okay. So let's look at multiprocessor systems. Within the past several years, multiprocessor systems, also known as parallel systems or multi-core systems, I just mentioned it now, have begun to dominate the landscape of computing. Such systems have two or more processors in close communication. So multiprocessing system consists of having more than one CPUs that interact in achieving the task. So now, where is because we also had extra special purpose processors when it came to single processor, but where is the difference between multiprocessor and single processor is that with multiprocessing, we can have the same instruction, one instruction, part of it being handled by one CPU, another part being handled by another CPU concurrently. And in the end, the result are integrated because the two CPUs are communicating to each other. They're in interaction to produce the outcome. But in a case of a single processor, although we might have a CPU and a separate special function processor, each one will have to start its own instruction and finish it. They do not share concurrently the execution of a single instruction. So there's no common instructions. Is that okay? Okay, so that's very important. The main benefits of multiprocessors are as follows. Increased throughput. Of course, you perform more tasks per time. For the same amount of time, a multiprocessor system will process more instructions or tasks than a single processor. Economy of scale. Multiprocessor systems can cost less than equivalent multiple single processor systems. What does that mean? If you were to have multiple single processor systems, meaning multiple computer systems, which are all single processor, meaning the two CPUs are not residing on the same computer system. You can still achieve some level of parallelism, but that will come at a higher cost that compared to when you would have the two processors sitting on the same computer system. Okay, so that is what we call economy of scale, because in one case you'd have two power supplies. Everything will be duplicated when you've got two single processor systems, compared to a multi-processor system whereby all of these resources, power supplies and so on, are commonly shared between the two CPUs. The third benefit of a multi-processor system is what we call increased reliability. Because we've got multiple processors, should one fail to execute a task, another one can take over. And that improves the reliability in the sense that you are almost sure that an instruction will successfully execute. Okay. Okay. So that is increased reliability that we get in that case. Okay. So very important. Increased reliability of a computer system is crucial in many applications. The ability to continue providing service proportional to the level of surviving hardware is called graceful degradation. So in a multiprocessor system, it's exactly what I just mentioned. If one of the components was to fail, one of the CPUs was to fail, there's still a graceful degradation in the sense that another one can take over. Okay. Some systems go beyond graceful degradation and they are called fault tolerant. So faults can happen, but you almost won't even feel them because they can suffer failure, and I've explained that, on one component and the other one can continue. Okay. So that's very important to mention. The HP non-stop formally tandem system uses both hardware and software duplication to ensure continued operation despite faults. So that's a typical example of a fault-tolerant system, multiprocessor system, HP non-stop, as it's called. Okay, so I think the concept of single processor multiprocessor is quite clear in that sense. Okay. The multiple processor system in use today are of two types. We get what we call asymmetric multiprocessing, in which each processor is assigned a specific task. So one task per processor. A BOS processor, which is more like a manager, controls the system. The other processors either look at the BOS for instructions. They are more like, give me an instruction, requesting instruction, and the BOS allocates, basically. They execute and they return the result to the BOS, which coordinates. At the end of the day, that's asymmetric multiprocessing. The alternative is what we call symmetric multiprocessing, or SMP, in which each processor performs all tasks within the operating system. So the task can be shared among processors, basically, at the end of the day. I will conclude there for today. And the picture in figure 1.6 shows a symmetric multiprocessing architecture. As you can see, memory is common to all of them. We've got multiple CPUs. First of all, that's what makes it multiprocessing. It's symmetric because any of these CPUs can handle any task. And of course, within CPUs, we've got internal registers and some cache memory. Cache memory, which is a transitional memory. Okay. Unless there are any other questions, we'll call it a day for today. I'll see you tomorrow for further class, and we'll try by tomorrow actually to go faster. I will have prepared slides, and then we'll go faster and try and finish this chapter. Any questions? Maluleke? You can also use the chat for questions in case you have any.
Sir.
Yes, go ahead.
I wanted to ask, you mentioned something about the hierarchy of systems when you spoke about the mini computer, the servers, and then you spoke about
Mobile.
Yeah, so I wanted to ask, between that and the supercomputer, the mainframe and the supercomputer, what differences are there, and which one is higher in the hierarchy?
Okay, mainframe will be, because it's really at data center level. The supercomputer is still not the mainframe. Mainframe will be higher. That's what I'm trying to say.
What would be the difference from the two?
Okay, storage ability is one of the major differences. The one is focused towards beta processing, that's a supercomputer, but the other one is more focused towards beta storage.
Oh, okay.
That's why I say mainframes will normally be used in data centers, for example.
Oh, okay.
Where you store large volume of data.
And what about a server? In a server and a supercomputer?
Okay, a server and a supercomputer, the difference will be supercomputer is still dedicated more or less to one user. It's more of a one user computer. A server is a multi-user computer, but they're sitting more or less at the same level.
Oh, okay. Okay, it's understandable. Thank you.
Thank you. Okay, I'll see you guys tomorrow. I'll share the video of yesterday and of today through the same link while I investigate the ability for you guys to download it on MS Teams. Thank you. Cheers for now. Bye.